Good afternoon. We will start our session with a short video that we prepared for the InnoTrans, and then we will introduce the session with the IP coordinator Antonella Trombetta. Please, Pauline. Thank you. I forgot to mention that as this video was made for InnoTrans, it has no sound. So you saw in the video you saw a small summary of the IP2 program. The areas that it covers with the technical demonstrators, like smart fail-safe communications and positioning systems, traffic management evolution, automation, moving block and train integrity, and smart procurement and testing, and virtual coupling and cybersecurity. You will see presentations in the topics of onboard train integrity and integrated technical demonstrators and automatic train operation traffic management systems, smart radio connected wayside all-in-all wayside objects, and you can have an overview of our open core projects, AB4 Rail, Performing Rail, Optima, and Smart 2. I would like to give the floor to the IP2 coordinator, Antonella Trombetta from Touch Area. Please.
Good afternoon. I hope you can hear me without problem. Yes, I'm Antonella Trombetta. I'm the IP2 coordinator, and now I would like to spend a few words about the IP2, even if the video explained in a very proper way, which is what was and is still the challenges of IP2. We suppose that the innovation program 2 was and is to upgrade the control, command and communication system. We supposed to have the CCS to become a flexible, real-time, intelligent traffic management and decision support system. It is not an easy task. There were a lot of companies that helps and put a lot of effort to reach all the goals. As Matthias said before, and also was quite clear in the video, we are speaking about 11 technical demonstrators, different technical demonstrators. But even if they are different, there are different leaders and so on, we need to consider that are all fully interconnected. The common topic of everyone is to increase the performance in a sustainable way. Matthias already mentioned the ATO. This is one of the, let me say, most important technical demonstrator, because the specification of the grade of automation 2 will be in the next TSI, and so the new challenge will be to the deployment of what was studied in the IP2. What can I say? We can say that the ATO and the moving block has the aim to increase the performance. We have the adaptable communication system that is the basis for the future rail, especially considering the interconnection and the wireless configuration. This will help again the train integrity, the moving block, the smart object wayside object controller. Sorry, and of course, if we are speaking to a broad and a broad implementation of this new type of communication, we have to think about cybersecurity, and we are very proud to have inside our IP also the technical demonstrator related to the cybersecurity. Then we have also two other technical demonstrators. That one is for the zero test on site and formal methods, that has the aim to standardize the test and also the specification, and it will reduce a lot, especially for zero test on site, the effort of the test along the line, with some disruption on the normal management of the line, but of course reduce of it's more a cost efficient approach. Then we have the upgrade of the traffic management system in order to have automated process management, a lot of data, also with the other sectors that are connected with the rail, and this is for us the starting point also for what we call the mobility as a service. We have also two other TD that are probably more innovate. Yes, it's more related to the innovation, that are the virtual coupling and also the train positioning, including the satellite. Just to finish my intervention, really key challenge for IP2 is to enhance the advanced traffic management control system without affecting the ERTMS core, because in this case, really we need to build, or we supposed to build the overall innovation on the ERTMS that already exists, and we suppose to have it in place in the near future. So I think that now I can leave the floor, and I hope you will enjoy the topics that will be the future of our rail. Thanks.
Thank you. Thank you very much, Antonella. We will continue with a few sentences about our housekeeping rules today. You may notice that we restricted the microphones and the cameras. If you have questions, please put it in the chat box. And at the end of all presentations, we will have a Q&A session for answering all the questions. And you, as you may see, and as you may notice in previous sessions, that this session is recorded also. So I would like to give the floor our first presenter about the onboard train integrity topic, Salvatore Iombino. Please, Salvatore.
Good afternoon. Thank you, Mattias. My name is Salvatore Danilo Iovino from Itachi. I'm leader for this project since the beginning, so now 7 years, now towards this the conclusion in December this year. Please, Pauline, next slide. Okay, the keyword for this project is onboard, which means implementing chain integrity without no more using trackside detection elements. Double is the benefit for this approach, for this onboard approach of the chain integrity. On one side, cost reduction for the infrastructure that is widely simplified in this way. The other side is also enabling the capacity increase by enabling technologies like moving blocks, virtual blocks, and in the end, the TCS level 3. Next, Pauline. Thank you. The project defined since the beginning 3 different product classes for different kind of trains using 3 different criteria for the train integrity. First class is about new generation trains or any kind of train with a wired onboard communication network. In this case, the integrity criteria is quite simple: liveliness of the communication between head and tail. Classes 2 and 3 addresses trains where no wired network is available, so wireless link has to be used. In the class 2, kinematic data from head and tail are compared and exchanged over radio. It can be like regional applications, for instance. Class 3, more appropriate for freight trains, for instance, is able to detect more accurately where the separation occurred. The criteria is detecting separation between adjacent wagons, and we will see 3 different technological demonstrators that implemented the 3 classes. Next, please. The work was, since the beginning, complemented always by a safety analysis. One of the results of this work included the evaluation of the quantitative evaluation of the tolerable hazard rate. This work has been led by Relenium with support from 4 railways that provided data from 10 years of service in the different networks, Deutsche Bahn, Network Rail, ÖBB, and SBB. The criteria was simple, like here shown. Hazard happens in case of a fault to a failure to a coupling and a failure to the OTI system. Result is that SIL2 is the appropriate target. Next, please. In the last year, the work has been complemented by a performance analysis done in the laboratory with 2 different simulators, giving guidelines to the demonstrators before going on field. Here we can see the simulator from SEIT, San Sebastian, that modeled in their simulator the Italian line selected by Hitachi for the testing on site, and the specific chain ALN 668 for regional service adopted. The simulation was focused on the speed comparison between id and tail, and to give specifically parameters, which parameters are more appropriate to ensure a complete false alarm filtering. This was the work from SEIT. Next, please. Complementary work by Relenium with the UPAL model, a complete simulation of the OTI finite state machine, focusing on behavior of the system respect to the communication part. We've seen that we have wired or wireless technologies in the 3 classes. And here we can see, thanks to this simulation, for instance, results about the detection time for detecting loss of integrity, but also probability of false alarms to give the performances of the system in advance, depending on the loss message rate. Next, please. Okay, now we can see the 3 demonstrators. AZD selected the class 1, which means wired communication, Ethernet link specifically, OTI device installed in each wagon, and implementing chain integrity and also chain length determination. Like all the 3 demonstrators, the 2 functionalities are available. A dashboard allows observing OTI system behavior and reconfiguring it when the chain changes its composition. Next, please. As they made the testing in the summer, in August this year, in a line operated by AZD itself in experimental chain, equipped in a simple way with the Ethernet link, as we have seen. The testing included the chain integrity and chain length determination. Chain length is based on configuration parameters preloaded in the OTI device in each wagon, so are used as part of a chain composition detection procedure. Monitoring included different kind of joining and split scenarios, loss of integrity, and recovery of the communication when it's temporarily lost. We can go to the next. This is the class 2 demonstrator from Hitachi. Thank you, Pauline. Yes, you can start the animation. Okay, so the experimental chain from Hitachi has been provided and prepared with the support from Trenitalia that provided 2 locos ALN 668 for regional service. The installation has been done in Sulmona in September-October with an equipment composed of full ETCS equipment, an adaptable communication system gateway, a radio able to communicate over public communication cellular network. We can see the antennas on the roof of the train here, and OTI rack with 2 coupled locos. The testing has been done in November, some nights in November, with the support and the coordination with the Trenitalia in Pescara Ortona. The testing included the communication with the TMS in a pairing phase, then chain length determination that consists in measuring chain length by acquiring a balise with hidden tail. Then the monitoring itself, that in this case is made up of 2 parts. On one side, comparing the speed, as we have seen already in the simulator from SAIT. And also, and was mainly focused on checking the good behavior for filtering false alarms, and it worked properly. The other part is about the communication. We can see in the picture on the right 2 tunnels, 2 free tunnels, longer one near Ortona, where the connection is not available. The cellular public network is not available in the tunnels. And here the testing confirmed the expected behavior and compliant with the specification change request 9040. When connection is lost, chain integrity becomes unavailable, which means for a radio block center, virtual occupation of the chain is increased and the tunnel appears occupied. When the communication is restored, then again chain confirmation is provided and the tunnel becomes again non-occupied. We can go to the third demonstrator from Indra for 3 trains, testing done in UK with network rail. In this case, OTI device is installed in all wagons, multiple sensors adopted for the separation detection, radio signal strength, IMU, GPS, chain length based on chain composition phase, network topology discovery approach, and comparison with data provided by the TMS itself. 3 testing sessions done in April, September, and October in UK. We can go to the next slide and look the video from this testing.
This is the first day of our trials for the X-Rail 4 train integrity monitoring system.
Train integrity is how you know the train is still together. So how does the driver at the front of the train know if the carriage at the back has slipped off?
We install sensors in all the wagons and locomotives, and these sensors are going to send data to a central process unit.
The idea is just to confirm that the system is properly configured to detect a break of integrity in a safety way.
As we progress through ETCS level 2 into ETCS level 3, we will likely no longer have train detection by the line side.
So we need a method to determine the train is in one piece or not. Without relying on track side infrastructure, that is where Indra's equipment comes in.
ETCS Level 3 moving block requires the completeness of the train to be determined on board, known as onboard train integrity. These trials feature a wireless solution with freight trains in mind. Wireless nodes are fitted to each wagon. Successful communication between the nodes confirms integrity and determines the train's length. If the train separates, loss of integrity is detected and reported to the radio block center. Based on the previous location of the train reporting integrity is confirmed, the radio block center will determine the extent of occupied track and protect the following train by withholding any further movement authority.
Currently, we have everything controlled. We have back of the train is give us all the necessary data to make the first step of slip.
We slipped the wagons for the first time in the testing. It was a success. And now we have just gone back to reconnect the wagons.
We're going to perform another slip test. Michael will operate the controls and the trains will separate. So you can see now we've slipped the wagons and the brakes have come on, so we're moving away from them. That was a successful slip.
During testing, the integrity monitoring systems being trialled promptly detected the separations and indicated train length. This integrity detection supports moving block by communicating integrity status and train length to the radio block center when operating in ETCS Level 3.
We are collecting data that is really important because with that data we can use it for future improvement.
We've had a great week on this heritage railway doing this testing, and just the adaptability of everyone has really helped this testing pull through.
Okay, then to complete, DLR developed a migration plan, which means how to perform the rollout of the developed technologies in real service. This work has been done by considering an abstract network derived from a real network in Austria. This piece of network is in detail characterized by different kind of density in each line, different number of trackside detection elements, and heterogeneous fleet of trains traveling on it. The analysis consisted in considering a scenario of 6-8 years and evaluating, this is the keyword in a migration plan, which is the best, more appropriate order or equipping the trains for ensuring the fastest reduction of the trackside. How early as early as possible, removing the trackside elements. And this work is here shown in a simplified way. From year 0 to year 8, we can see the green color describing a line where no more detection elements, trackside detection elements are there. This work will be soon available as a public document in early 2023, and also presented in Railgrad next year with a paper. We can then complete, Pauline. Okay, results. In conclusion, in the last year of work, the safety analysis started since the beginning, has been here complemented on the specific demonstrators, on the specific developments done this year. Before going on site, we had, like in a zero-site testing approach, results from the lab, anticipating the performances of the system and giving guidelines about how to configure properly the OTI integrity criteria before going on site. Finally, we've seen 3 successful experiences of field testing with the 3 different kind of classes defined in the beginning, with the chain integrity, but also with the chain length determination. All this work, as we've seen, has been complemented by a migration plan to say how to roll out these technologies. The project is now going to its conclusion in this month. In the next slide, we can see all the partners. Thank you to all the partners that contributed in this final step of the project to reach all the objective of the project itself. Thank you. That's all.
Thank you very much, Salvatore. I would like to ask. Thank you for the presentation. I would like to ask everybody to put questions into the chat, and Salvatore can answer them in the question and answers session. Please also don't forget to address the question to the presenter. Then we can easily find the best person to answer them. I would like to ask. I would like to give the floor to Richard Deacon in the topic of integrated technical demonstrator. Please, Richard, start your presentation.
Matthias, hi, thank you. Good afternoon, everyone. I'm delighted to be here today to present the ITD, a project which Network Rail volunteered to lead when we put in the Shift to Rail proposal some 6 years ago, nearly. I'll also include Technical Demonstrator 2.1, Adaptable Comms, and Technical Demonstrator 2.3, Moving Block, on behalf of Ulrich Gier and Simon Chadwick as well. Next slide, please. So the Integrated Technical Demonstrator is a combination of 3 different work streams in the IP2 program in Shift to Rail: adaptable communications, moving block, and onboard train integrity, which you've just heard about. All 3 projects started their work back in 2016, developing specifications for their outputs, which could be developed and delivered as technology demonstrators towards the end of the program in a real-life environment. Next slide, please. So we're just going to take a very quick look at the ITD system diagram to give you an idea of what it looked like. So the yellow boxes are the new equipment that we used, and the dark blue box there are the boxes that we modified with the software. So the bottom left-hand box is the Class 313 train. The next one up, the pink box, is the Class 717 train, which had the majority of all the modifications done to it. Beside that, we can see the ACS cloud and server. And to the right-hand side of the diagram, we can see the ENIF control, where we ran the tests from and controlled things. And then you've got all of the different lines of communication which connects all of these different bits of equipment up. Next slide, please. So looking at ACS, the ACS system definition or specification was updated, and the field tests were performed to validate the ACS concepts in a real environment. So these were the mainline high-speed demonstrator with SNCF in France and DB in Germany, the urban suburban demonstrator with Network Rail in the UK, and of course the ACS as part of the integrated technical demonstrator with Network Rail in the UK as well. Next slide, please. So for the field test for mainline high speed with SNCF in France, the tests were performed successfully on the test track from Paris to Marseille in Q2. And with DB, tests were performed successfully in Living Lab in Erzgebirge in Q4. Next slide, please. So Siemens successfully tested on the ENIF test track in the UK in Q2 using various bearers, including GSMR, LTE, Wi-Fi and 5G. This was completed initially using the Class 313 test train, and these tests gave us confidence of the solution before we integrated the technology onto the Class 717 passenger train, combining with the moving block and the train integrity in the ITD demonstrator. Next slide, please. And there are field tests planned for regional and freight on the Novara row at RFI in Italy in January 2023 using LTE and SATCOM. Next slide, please. So the ACS benefits. There are many benefits, as you can see in the slide. and advantages for ACS, but the biggest one for me is the improved connection reliability through higher redundancy. ACS is all about enabling switching between the telecoms bearers to make sure that there's no interruption in providing a service to users. Next slide, please. So luckily, you've already seen the OTI video, and it showed why we need OTI to operate all of the trains on the network if we're going to plan to use the ETCS level 3. The OTI, you can see in the bottom of the picture in this one, the special sort of slip device that was used. That's just a more in detail sort of look at that. This was connected between the loco and the wagons to force them apart when moving. So you can see if the kit developed to monitor the train integrity and the length could pick up that the train had actually slipped. And after showing this worked, we brought the solution forward into the ITD, where we simulated the OTI input into the ETCS onboard on the class 717. Next slide, please. And finally, we get to the moving block. So first, I need to provide the update for the TD 2.3. This slide shows the progress of the moving block through the XRL program. So from XRL all the way through up to XRL 5. Next slide, please. So the status of the XRL 5 work package 4 moving block deliverables is shown on this slide. D4.1 moving block specification is expected December 2022. 4.2 is the moving block enhancements, which is expected in May 2023, and the D4.3 report for moving block technical demonstrators is expected December 2022. Next slide, please. And as you can see here, there were 3 technical demonstrators: Siemens in Madrid, Hitachi in Genoa, and Thales in Berlin. And these were laboratory demonstrators with simulation of trackside and the trains. Next slide, please. So now we can move on to the ITD, which pulled moving block, OTI and ACS together. It had some complex requirements to enable us to demonstrate it in real life. We needed the 2 trains fitted with ETCS that could have the software upgraded, as well as ACS and OTI fitting. We needed an ETCS level 3 trackside enhanced with ACS. And for this, we used Watton at Stone, and we controlled that from the ENIF. We needed a safety case. Running 2 trains controlled by software and technology under development on the operational railway, albeit inside the test track, had some risks which we needed to manage. And then, of course, we needed qualified test train drivers and testers, as well as track access. So an awful lot to pull together and integrate before we could actually get close to running our first test. And of course, we captured this on a short video, which I'd like to show you now. So if you go to the next slide, if you could run the video for me.
Work Package 12 is the integrated technical demonstrator for the XRL 5 program.
The integrated technical demonstrator is an integration of 3 technologies:
So
adaptive
Mattis,
communication system, onboard train integrity, and moving block.
It's a class 313, and we also have to our left here.
We repair it in a minute. Sorry.
Okay, that's okay, thanks. So now I just think we need to get the sound. Smashing, thanks.
Yeah, now
Work Package 12 is the integrated technical demonstrator for the XTRL5 program.
The integrated technical demonstrator is an integration of 3 technologies: adaptive communication system, onboard train integrity, and moving block.
It's a Class 313, and we also have, to our left here, Class 717, leased by Rockrail to GTR.
The success of the integrated technical demonstrator proves the concept of moving block, using radio-based ETCS for communication between train and trackside, using an onboard train integrity device which monitors and communicates the completeness of the train via ETCS to the trackside.
We're going to roll down the track and do bearer switching between LTE and GSMR. The whole point of this is reliability, so you'll always have live connection.
Yeah, the GSMR is down. Yeah. Now only the LTE. I was really happy to see the ACS is working. The GSMR is switching to LTE tunnel and back. That means that our ACS system is compatible with the Train 717 without any additional hardware changes.
The adaptable communication system was used, allowing for safety critical information to be sent continuously to the train by using multiple bearers, which include 3G, 4G, 5G, Wi-Fi, and GSMR.
There are 2 trains during the ITD. The 717 will simulate an integrity loss using the onboard train integrity. The adaptive communication system will send this to the trackside, and that will then inform the 313's following and adjust its movement authority so it stops in a safe place in the simulated environment.
To communicate with the cloud, we use the ACS. The integration worked perfectly in a transparent manner. In the integration with the train, it went perfectly also as we expected.
As well as the team on the train today, there was also a shifter rail team working at ENIF.
Moving block is a type of railway signalling that allows the benefits of higher train capacity with maintained or reduced trackside infrastructure costs.
Moving block can meet these objectives by using information transmitted from train to the trackside within ETCS. Track sections previously limited to 1 train can now be allowed to contain multiple trains, each within their own moving block.
Instead of operating in fixed block, as you would be with colour light signals, we've been operating in moving block to prove various concepts.
If they lose communication with the front train, they assume that it's where it was last recorded. They don't extend the movement authority.
These 3 systems are essential in order just to develop an ETCS level 3. We will increase the safety because at the end we have a continuous register of what the train is doing.
The integrated technical demonstrator is a networker-led project, but its success was only possible due to the collaboration of several railways and suppliers.
What we have is an interoperability demonstrator, which I think is very good for Europe and for all the different partners in order just to work in the future.
Without all of the people we mentioned, we couldn't have done what we've done, and we've achieved a massive amount. So a massive thank you to all.
Thank you. Next slide. So whilst I wait for the slide to come up, achievements and challenges.
Yeah, sorry, just it's when you stop sharing, and it will be a bit confused. Yes, thank you.
Okay, so the ITD was successful. We achieved the objectives set by Shifter Rail and demonstrated that we have specified and delivered solutions for ACS, OTI, and moving block. And I know our shifter rail partners are absolutely delighted with the results. And I've thoroughly enjoyed working with them over the past few years. So this wasn't easy to achieve, and we had multiple challenges to overcome. Delivery dates for outputs from different partners kept changing. We had issues booking trains and track access, and we're making sure that we had the required competent resources to support the site activities. Just when we thought we perhaps finally had an agreed integrated plan, something else would happen, and we'd have to manage the change again. And all this whilst we were dealing with COVID. So next slide, please.
We'll fix it in a minute, sorry.
That's okay, Matthias. There you go. So I'd like to finish by recognising that this project has delivered more than just technical results. The collaboration, the teamwork, the commitment to deliver by everyone on this project, some of whom you can see in the photos on the slide, it is a fantastic achievement in its own right. So a big thank you from me to everyone involved, and well done. And next slide, we'll show you the logos for the companies that were involved. Thanks very much for your time.
Thank you very much, Richard. Sorry for the technical problems, but it's always when we change the media, then it's happening. Thank you for the interesting presentation. And now I would like to give the floor to in regards the TD 2.2 automatic train operation to Benoit Bienfait. Please, Benoit, introduce yourself in two sentences, and then please give your presentation. Thank you.
Thank you. So my name is Benoit Bienfait, working for Alstom. I'm currently design authority for ATO over ETCS in Alstom. And in addition, I'm leading since the beginning the TD 2.2 of Shift2Rail. The aim of this TD 2.2 is to achieve standard specification for ATO up to JOA 4. In addition, I'm also leading the ATO work package for UNISIG. You can go to the end of the slide. You can click several times. Yes, once more, once more, once more, and once more. Voilà. So on these slides, you can see that what we are doing in the TD 2.2 is the logical continuation of the big standardization process started a long time ago now, and going through the different grades of automation. You can see on the bottom, on the left, it is the JOA 0. The driver was alone on the train, the only boss after God. Then we had the JOA 1. The driver is still there doing everything, but is controlled, supervised by the automatic train protection, for which all of our companies have spent a lot of time to standardize what is now ETCS to define interoperable and interchangeable solutions. Then we have the JOA 2, which is the first big achievement of the TD 2.2. JOA 2, the driver is still in the cab, pushing a push button, and the train is driven automatically at the next station. The driver is still there to detect the obstacles and to manage to secure the entry and exit in station. And so we have worked a lot on that, and the achievement now is that we have the standard specification via different subsets. I will not detail that today. And these different subsets, this specification will be in the TSI 2022, which is in the final stage now. And then we are continuing until JOA 4. We are working in X2REL 4. The aim of this work is to give the final specification for ETIO up to GE4 in December 2023. What we are doing is to define the standard architecture with interchangeable building blocks with triple FIS interfaces. And in our remit, we have also to be aligned with what is known about OCORA NRCA. We have regular meeting with OCORA people to achieve only one common standard architecture. The outcome of what we are doing in the TD 2.2 will be used in Europe's rail in large-scale demonstrator. You can go to the next slide, please. This is the timescale of the GE2 achievement, which is, as I said, very important for Shift2Rail. We started actually in March 2012, already before Shift2Rail. The first specification was approved by the agency, European agency, and the partners in September 2014. We have frozen the specification to perform the first specification in September and is approved by ERA in March 2018. We have frozen the specification to complete the factory test on two reference test benches, one in Siemens, Berlin, and the other in Alstom, Charleroi. On these reference test benches, we have mixed the different product tracks that are on board from different suppliers to demonstrate the interoperability. That was in January 2019. In December 2012, we have completed that on two pilot train and pilot test in Switzerland for freight train and in UK with the class 313. And so after that, we have detected the findings coming from these specifications. We have updated the subset and we have received the agreement of the partners in ECT meetings with ERA in March of this year, ready to go to the TSI 2022. You can click, so we include the findings, as I said here. You can go to the next slide, please. This is time scale for the GE3.4 specification. By the way, it is ETIO up to GE4 because this architecture continues to support, of course, GE2. We started in September 2016. The first specification were frozen in September of this year, frozen to be used for the prototypes that will be used for the pilot test. The factory test will be done on two reference test benches, one in Hitachi, Genoa, and the other in Alstom, Belgium. These factory tests are foreseen in between March and June 2023. While the pilot tests on site are foreseen in September of next year. The pilot test will be performed on an AZD train and AZD line facility. The final completion of the specification is expected for December of next year. And the outcome, as you can see, is the standard architecture, which is already now fixed with building blocks agreed between all the partners. These building blocks are fully interchangeable, can be supplied by different suppliers without any problem with plug-and-play interfaces which are specified. Can go to the next slide, please. Yeah, you can click several times if you agree to accelerate a little bit. Yes, once more. And once more. Yes, thank you. On this slide, you can see it is a global representation of the behavior of an ETO. The ETO over TCS is based on a track-train communication, which is fully interoperable, where the onboard is always requesting data from track side and is receiving two types of information: the timetables, the operation information, what we call journey profiles, giving the next timing point, passing points, and so on. And also the infrastructure data, the track plan data coming from the digital map track side. Starting with this information, the onboard is able to compute an optimum speed profile, permitting to arrive strictly on time, but minimizing also the energy consumption. So the main benefits of an ETO are first the operating cost. the energy savings, of course. We cannot give you figures today because the figures are not the same for the different suppliers. The optimum speed profile is still supplier specific. And so the values that we can achieve are today different from one supplier to another. But you will see just after some graphic representation of what we can achieve. So at the network level, the benefits are first the capacity increase for two reasons mainly. The first reason is that the ETCS is changing its behavior according to the fact that the ETO is engaged or not. When ETO is engaged, the ETCS is removing all the reaction time due to the driver. So it is around 10 seconds, it depends on situation, of course. And this reaction time permits to reduce the minimum headway between two trains. The second factor is the fact that thanks to the fact that the ETO behave always in the same manner, it's possible to reduce the dispersion in the driving styles, driving for the interstations. And so as the different operators are building their timetable on a statistical representation, the fact that the dispersion in the travel time is reduced, they have also to reduce, they may reduce the margin that they put in the timetable today to manage this dispersion in the travel times. These two effects permit to reduce the headway, minimum headway between two trains. And so it's possible to operate more trains by time units on the same line without any investment track side. This is also one of the most important benefits. Once more, we cannot give figures today because it is not yet agreed by the different suppliers today. They achieve different performances today. And the last type of benefits is the quality of service. So running on a train on time to an increased timetable is indeed one of the major effects also of ETO. You arrive always on time, except if your train is completely degraded, of course. But if there is no big degradation in the train, then you arrive always on time. Even if you have less traction capability, for example, the ETO will always try to recover the timetable if it is possible. And last but not least, the impression of comfort is much more great with an ETO than a driver. You can go to the next slide, please. Yeah. On this slide, you can see why we have energy savings. On these slides, you can see on the upper drawing, you can see it is a graphic giving the speed profile with on the bottom the distance traveled by the train, and in the ordinates you can see the speed. And so you have on this drawing different lines. The higher ones indicate the maximum static speed profile to be guaranteed for the safety. And so ETO first is connected to ETCS, so the ETO will never overpass the maximum train speed imposed by ETCS. This is the upper lines. Then you can see several lines. These are manual driving. So to perform this travel, and the lines in the bottom are the speed profile of an ETO, a train driven by an ETO. This drawing, these lines have been achieved using a simulator, the simulator used by the Belgian Railway to train the driver very close to the reality on a simulated line, which is also an existing line in Belgium. And we have worked with actual drivers coming from the Belgian Railways, and they have driven the train during a full day, each of them, to see, to compare their behavior with the behavior of an ETO. And what you can see on this drawing is that in general, for the same travel time, because we kept only all the measurement where the travel time was identical, more or less 10 seconds. So for the same travel time, you can see on this drawing that the drivers are looking for, searching for higher speed, but they start to brake earlier than an ETO, And in the acceleration process, you see also that it will accelerate differently than ETO. And so this is the reason why it's possible to make so much energy saving, of course. In addition, the ATO will always try to use the coasting capabilities depending on the slope on the track. The drawing on the bottom, on the left at the bottom, is for the same line. So in this case, it is more or less 30 kilometers. And you can see the accumulated energy consumption. You see on the bottom the drawing, the figure coming from ETO, and on the lines up are the manual driving. So we have not put the figures here because it is not common for all the suppliers, of course. But in this case, if you look, you will see more or less 12% of wind. And this is some tests that have been performed on long interstations with an yes.
Sorry, just I would like to ask you to a bit speed up just to keep the time frame.
Okay.
Thank you.
I have only one slide, do not worry. And so we can go to the next slide. The next slide is exactly the same simulation on the same line, but where the train is stopping everywhere, so with interstations of 2 or 3 kilometers. You can see the same several lines. On the bottom, always you will see the ATO ones, and the upper lines are the driver manual driving. The same phenomena you can see for the same travel time, the drivers are searching for higher speed. And of course, the impact on the energy consumption is much more higher because the impact of the driving style of the driver is much more important too. The driver is always starting and accelerating. So you can see on the bottom, the cumulated energy consumption, the figures are much more higher, of course. You can see more or less 45% of gain in this drawing, which is only from one supplier. So you can go to the next slide if you agree. That's it. So we can conclude, if you agree, just saying that according to the current status of the TD2.2, we can say that the ATO in JUE2 is now mature, ready for commercial operation, for the different type of operation. So the specifications are now frozen and will be part of the TSI 2022. And for the ATO up to JUE4, it is an ongoing work that will be completed in December 2023. Thank you for your attention.
Thank you very much, Benoit, for the interesting presentation, and especially for regarding the energy savings part, which is kind of a hot topic of today. I would like to ask Andreas Sölke to start with the TMS applications. Please, Andreas. Start with introducing yourself in 2 sentences. Thank you.
Yeah, thank you. I'm Andreas Sölke. I work at Deutsche Bahn in Germany, more specifically at DB Netz, so the German infrastructure provider, infrastructure manager, and there within the Digitale Schiene Deutschland program. So we are working there on the optimized railway operation of the future, and also contribute to the traffic management evolution work package. So work package 8 of X-Rail 4, which I would also like to show some results from. So especially about the opportunities and challenges of using optimization traffic management, because this is the central or one of the central goals also of this work package. We have different streams, so different tasks in that work package. One thing is that, in my impression, also traffic management is the least standardized process within the rail system. So we put some effort into also putting together some standardized use cases, also for faster international development of traffic management systems and also collaboration. And then we think about how to use optimization in traffic management, because actually it's not quite so easy, especially if you think about more large-scale optimization. Then you need significant changes in traffic management procedures and functionality. And in this task, we also describe a bit how they could look like and what challenges we have there. Then we look also into the actual doing of the optimization, so mathematical methods which evaluate concrete improvements of algorithms, and also have a collection of what could be the most promising approaches to apply it for large-scale optimization for traffic management. And when we look into the need for changing traffic management so drastically, we also need to look into how to keep the human performance high enough. So we need to assess the workload and situational awareness and the changing traffic management systems. And this is also what we're looking into. Yeah, next slide, please. So optimization, as usual, can have many different goals, and very often they are also contradicting. And also in optimization traffic management, this is the case also regarding energy savings. So the question is, how much focus do we want to put on energy savings as opposed to the other goals? So as we have already seen in the previous slides, this good connection to that. So we can travel as fast as possible, but that costs us more energy because we need to accelerate more. We could try to optimize the capacity, which is one of the central goals also of the plans. But that means we reduce the time buffers, which we could use to avoid braking, which is also wasting energy. And if you want to use regenerative braking, then that means it would be good to synchronize arrivals and departures. But then we also need to talk with the potentially different railway undertakings together with the infrastructure on how to do that. So this is hampering this freedom to plan independently. And also we have the ATOs, which, as we heard, wonderfully can optimize single train energy, but TMS wants to optimize the energy of the whole network. So we need to see on who is exactly responsible to plan on what detail there. Yeah, the next slide, please. Here's one example for that. So very similar pictures like we had in the last presentation. So again, train trajectories with the speed and the distance. In the upper picture, we have optimized it for speed. So that means, we travel always as fast as possible. And in the lower picture, it's very energy efficient. That means we just speed up as far as we can at that point and then coast until we have to brake again. So in the lower picture, we would not accelerate if the resulting travel time reduction would be low. But that means between those two curves, we need to find a compromise. And this is pretty hard to do manually. Next picture, please. So we need optimization. And academic research also shows that there is a lot of potential. Not directly energy optimization, but some other factors. So try to reduce the disturbances in general by automation of the traffic management, avoid unplanned braking, and also consideration of velocities and green waves. So there is a lot of potential. Most models could even be extended to consider energy directly or post-process it. But the question is mainly, if we already have so much academic work, why don't we just use it? Yeah, so next slide, please. This is because, we have so many works also in these European gremiums. So we have heard also here a lot about ATO and other ETCS, etc. But most of this is not there yet. So for applying optimization, we also need some preconditions, so especially the data quality. So machines cannot work with unreliable or incomplete data as well as humans can, which just interpret or interpolate the data. The technical equipment is important. So with more optimization, we can expect to have more and more frequent changes to the traffic plans. Might just be minor changes, but it is very beneficial to have at least a driver advisory system or even ATO to also do these plans, so drive the trains, and also get the data from the positioning and signaling systems, like we also heard. And the last point is that with optimization and more frequent changes, a lot changes also in traffic management. So the interaction between the infrastructure management and the railway undertakings need to be more frequent. How to communicate the changing plans better to drivers, or better even ATOs, and most of all also how to the traffic management itself changes. So it changes from iteration of solutions, because changes to that, because until now most work is manual. I will also detail that a bit in the next slide, please. So traditionally, the resolution of contracts is done by humans, which understands the situation. So it's one of the great human capabilities to do that up to a certain extent. So if you want to apply large-scale optimization, then this changes, because now the operators need to understand and analyze solutions and not just their own single changes. So we need completely different interfaces to do that, and also need to evaluate on how to do that. Yeah, here's just on the right hand side a small picture showing some draft user interfaces. So there, in this work package, we also put some work into thinking ahead on how traffic management could really evolve in the future. So not just so to benefit most of optimization, so not just small scale optimization, not just single orders, but or two-train conflict resolution, but going into real optimization of traffic management. Yeah, next slide, please. So with that, I would also thank my partners in this work package. Yeah, and also finish this presentation, and hand over to the next speaker.
Thank you, Andres. Thank you for the presentation, and I would like to give the floor to Maria Belén Lozada Ferreira about the smart radio connected all-in-all wayside object controllers. Oh, I changed it a bit. Smart wayside object controllers, the SWOC. Please, Belén.
Okay, good afternoon to all of you. My name is Belén Lozada from Tales, Spain, and I'm the work package leader of S2 Rail 4, work package 11, and work package 12. Smart Wayside Object Controller. Demonstrators are TL4 and TL6. I'm going to present you the TD2.10 Smart Radio Connected All-in-All Wayside Object, also known as Smart Wayside Object Controller, SWOC, located in the IP2, and composed of two projects, S2 Rail 1, work package 7, and S2 Rail 4, work package 11, and work package 12. First of all, I'm present a general description of SWOC and demonstrators, then the main result of S2 Rail 4 project, work package 11, demonstrators are TL4, and finally the contribution to energy saving of TD2.10. So in this first slide, we can talk about the objective of the TD2.10 is to demonstrate a solution of object controllers with the centralized approach to rail automation. This approach will be scalable from high performance lines to regional and freight applications. Although modern signaling system will have considerably reduced trackside equipment, this solution is still relevant, and at least interfaces to points and level crossing will remain another necessary interface. Therefore, a solution where wireless communication and locally derived power together with maximum decentralization up to the level of one object controller for every individual trackside object is used overcome the current disadvantages of cabling, etc., admits the master plan in terms of improved reliability, enhanced capacity, lower investment, reduced operating costs, improve standardization, and therefore simplify certification authorization, and for sure guaranteeing safety and security justifications. The main purpose of S2 Rail 4 is to develop and test the SWOC in order to check the functionality features and architecture defined in S2 Rail 1 project to fulfill the 2.10 objectives such as wireless communication, power supply in terms of energy harvesting and power consumption, Smart features are diagnosis management, maintenance management, and asset management, and cybersecurity as secure environment. Also different operational scenarios in terms of market segments, type of website element control, communication type, control entities, diagnosis and maintenance features, and power management has been defined. Considering that 8 different demonstrators has been defined in order to cover a large spectrum of suitable scenarios, with the intention of being able to test in greater detail and precision each partner dealing with concrete environment and external element. Therefore, each participant developed the demonstrator with characteristics and solution, and the result of the demonstrator and description of solution of his company are included in the demonstration report. Concrete environment and external element has been described by each company. The demonstrators are wireless low power object controller demonstrator by CAF signaling, track vacancy detection SWOG demonstrator of Siemens, cable-less railway embankment demonstrator of Alstom and Traffic Bucket, multiple network scalable SWOG carried out by Hitachi Rail, smart website object controller of Indra, gauge signal smart website object controller carried out by ACD, wireless advanced diagnosis, intelligence distribution, and low power consumption carried out by Thales, and new generation of adaptable wireless sensor network for website object in railway environments by Relenium. Next slide, please. As result of the S2 Rail 4 project, first of all, the coverage of requirements is described. During the previous TD2.10 project, S2 Rail 1 WordPack 7, the set of system requirements for object controller functions, including power and communication with the smart website object controller should consider, was identified. These requirements were marked as either mandatory, recommended, or optional. The requirements coverage of all demonstrators at TL4 in the scope of Work Package 11 is shown in the figure in percentage. We have 96% of mandatory requirements and 85% of recommended requirements and 46% of optional requirements. Additionally, the conclusion from the analysis of the result of the demonstrators at TL4, that is the laboratory environment, in the scope of Work Package 11, considering the main objectives defined in TD2.10 are wireless communication. The general correct behavior of the smart website controller has been successfully verified through a wireless connection. We have used Wi-Fi, Zigbee, 3, 4, and 5G, LTE, LoRa, Sigfox in the communication with interlocking diagnosis system, traffic management system, and level crossing. Power supply for the energy sources power system has been demonstrated, and the possibilities to save energy by using different power saving modes, for example, sleeping mode. In any case, we will go in more detail about that in the following slides. Diagnosis and maintenance management, thank you. The correct behavior of diagnosis and maintenance capability and enhanced diagnosis, including predictive maintenance feature, website object auto-discovering as software data downloading has been successfully verified. And with regard to security, end-to-end secure communication is guaranteed by implementation of protection measures aligned with TD2.11 and cybersecurity standards. Overall, the objective of demonstrated a solution of object controllers, smart website object controllers, realizing a decentralized approach to rail automation has been achieved. This Work Package 11 has finished in 2021. As present works, Work Package 12 involved the implementation and development of TLC's demonstrator. That means in a relevant operational environment. The current laboratory-based smart website object controller configuration has been transferred to real environments and supplemented with functions that could not previously be implemented in TL4. The Work Package 12 ends on 2023. Next slide, please. In this slide, we start with the contribution to energy saving from the TD2.10. First point, local energy harvesting. In this part, solar panel has been included in several demonstrators with batteries and power controller in order to provide local energy and to check an external power system interface for monitoring and commands. Also, electromagnetic energy harvesting, harvesting energy from ambient signals from telecommunication systems such FM, RCS, and or GSM-R frequency bands. That a novel concept for enhancing the performance of electromagnetic energy harvested based on focusing metasurfaces has been developed. Relation of energy efficiency, reduction of power consumption in smart wayside object controller and even in wayside object in order to attain a very low power consumption has been also considered. Design of SWOG with a state-of-the-art direct drive technology to ensure that efficiency is at its maximum. It is important to consider in this part the dependency with the wayside object type, that we need to keep the service level, etc. Next slide, please. And finally, the power and energy management. We have made a sleep mode implementation. That means energy saving modes applied to smart wayside object controller and wayside object. For that, we have considered that we use when rail-wide traffic is not expected. It may require adaptation of safety rules to be able to save energy in a safe way. And also transition to and from sleep mode should be done in this safety way. And this transition could be time-based for the activation, and also event-driven for activation and deactivation. Other point is route setting based on available energy. For example, choosing a route that gives fewer activities of point machines. And finally, we have enhanced energy management from SWOG. Energy that is stored and available to the smart wayside object controller in power supply system, batteries, etc., is managed in addition to the traditional power management. For example, we use commands for operation of the power supply system, messages for power, monitoring, receiving alerts, alarms, power consumption, measurements, and in general data for diagnosis to enable preventive maintenance and to perform predictive maintenance. Switching between different power modes, for example, what we have seen before, the sleep mode, could be managed also. Power management, even from the traffic management system, with the objective to save energy. And all of the also considering this management from SWOG that we have the sufficient energy for operation. Next slide, please. And these are the partners that has been involved in from the beginning the TD2.10, and now they are involved in the STURAIL 4 Work Package 11 that has been in, and Work Package 12 that is carrying on. Thank you very much to all of you. Thank you.
Thank you very much for the presentation, and also for again for the energy savings aspect of the project. Now we are closing that part, which is closed, which is about our main project, X2Rail, which is still running, X2Rail 4 and X2Rail 5. And so because all these technical demonstrators was performing its work still in these two projects. And now we have an outlook to our open core project, which is several times our more exploratory research, and so it's more less strict way, less strict restricted projects. So we will see our the first is the alternative bearers for rail, EB4 rail project. I would like to give the floor to Romeo Giuliano. Please introduce yourself briefly and then give the presentation. Thank you.
Thank you, Matthias. My name is Romeo Giuliano. I'm a professor in Guglielmo Marconi University, and I'm a wireless engineer, and I'm a professor of 5G and Internet of Things communications. So going back to the project, I'm going to present the AB for Rail. That is a project. Please, Pauline, if you go to the next slide. Thank you. Here is reported the details of the project. The main objectives is to identify alternative communication bearers for the adaptable communication system and study what communication protocols in terms of transport and application level is the most promising, is the most suitable for the rail application. The partners of this project are Radiolabs and the University Guglielmo Marconi, located in Rome. Please go to the next slide. Here is just the organization of this project. You can see that we have two work streams, work stream 1 and work stream 2. And I report also the work breakdown structure in order to see the activities performed in this project. You can go to the description of WP4. You can skip the Gantt. The next, please, Pauline. Next one, please. Okay, the work package 2 is related to the alternative bearers investigation. So in the next slide, you can see the objectives, that is to identify possible alternative communication bearers to 5G, for example, or to GSM. We analyzed the technologies reported in the table to the right, so optics, power line, IFT, HEPS, and other novel technologies. In the next slide, we can see the approach that we use to select the most promising alternative bearers. We consider the scenario, that is the rail line, for example. We consider the ACS traffic class, and we consider the features of the communication technologies. From our analysis, we selected LEO satellite, HEPS, so high altitude platform station, and free space optics as the most promising alternative bearers. You can see in this slide the for each of them, you can see the architecture and some performance results in terms of throughput and latency. You can see, next slide, please, Pauline. Going to the work package 3, that is dedicated to the analysis of communication protocols. We investigate which is the best couple between transport layer and application layer protocols for specific rail applications. In particular, if you next slide, please. We developed an emulator that consider the wireless channel, the entire communication channel. So we consider a variation of latency, packet loss, available bandwidth at layers lower than network layer, so considering access and transmission within the core network. And over this emulator, we implemented the transport protocol and application protocols in order to transmit data from onboard train to the remote control center. Next slide, please. Here is the assumption and the sources we consider in our evaluation. So we consider a different type of traffic sources, constant bitrate such as videos, variable bitrate such as Skype or video call, a file transfer in order to provide file upload and download file, and the periodic message transmission in order to simulate ERTMS traffic light. We consider TCP in several versions, UDP, stream control transmission protocol, and QUIC concerning the transport protocol, and HTTP and FTP with their secure version concerning the application protocols. Go to the next slide, please. In order to consider a real railway scenarios, we consider these three cases: the Rome-Florence high-speed line and regional line, and also we consider the urban metro located in Rome. Sorry. You can see to the next slide, please, Pauline. Here is just a few results. You can see the average throughput on the left with respect to latency. So we increased the latency and we compared the throughput provided by transmitting data using TCP with the cubic version or BBR, QUIC, stream control transmission protocol, and the second version of QUIC. We can see in the second picture, we consider the same protocols, but varying the path loss along the line and in the and in the network. While in the pictures, in the graphs reported to the right, we can see the average throughput, not the average, sorry, the CDF averaged by several trials in the line from Rome to Florence with respect to latency and packet loss for all the five considered transport protocols. In the next slide, we see the application protocol considered. So this is HTTPS, and we provided the data with respect to download time of different pages. One small page with 1 megabyte and a larger one from 4 to 10 megabytes. You can go to the next slide. This is just a comparison of messages delays with and without TLS. This is just to consider when the security is implemented into transmission of the messages. We can go to the last work package that is dedicated to the dissemination activities. and we performed, we disseminate the activities performed in the IP4 rail in several social media profiles open ad hoc for this project. You can go to the next slide, please. You can see the project website. We open a YouTube channel, Twitter, LinkedIn, Facebook, ResearchGate, and we also involve my personal LinkedIn and Guglielmo Marconi website and magazine. Going to the next slide, please. Here there is some animation, so you can go quick. Thank you. This is just some activities we performed in the dissemination. So we participated to the Connecting Europe Express. We organized a workshop, a webinars. We presented 5 scientific papers with the results, and we are going to organize the final dissemination event in the next 21st of December. So you are invited to participate. Finally, going to the conclusion. We implemented, we investigate the most promising technologies as alternative bearers. The free space optics is not so stable, and it is more suitable for the station, remote stations. LEO satellite is quite good to provide the connectivity in remote areas, as well as HAPS. Considering HAPS, we assume that an LTA user equipment is mounted on board, so performance is not so good, but it is due to the limited transmission power and the distance of the HAPS. Concerning the transmission, the transport and application protocol, TCP, BBR, and QUIC are the most offer the better performance, but QUIC is not so standardized. So concerning the last work package, dissemination activities gave a very positive feedback. So I'm finished. So go to the next slide. This is the last slide. Thank you.
Thank you very much, Romeo. And I would like to give the floor Lei Chen, Professor Lei Chen, about the Performing Rail project. Please.
Yeah, thank you very much, Matteo. So my name is Lei Chen. So I'm a professor in the University of Birmingham, UK, and I lead our railway operation and control team in Birmingham Center for Rail Research and Education, and also in the Ukraine, the UK Railway Research Network. So today I'm going to share some of the progress of our EU project, the Performing Rail, the performance-based formal modeling and the optimal traffic management of moving block railway signaling. Next, please. So the project aims to delineate through the formal modeling and optimized traffic management and also moving block railway signaling using the advanced train positioning approaches that mitigate potential hazards in the diverse market segment, especially for the moving block systems. Next, please. The objectives in Performing Rail would be summarized into the below 8 points. The first is the definition of the specification for safe and performing moving block operations, the formal modeling of moving block specifications, identify of moving block hazards, and the development of fail-safe train localization solutions. Next, please. And also design of future traffic management architecture for moving block, the implementation of the moving block testing platform, and also the assessment of the moving block specification and model. Finally, we will give recommendations for safe and performing moving block configurations. Next, please. So we've got a good consortium members across whole of the Europe. We've got 8 members. You just need to press next. Next, please. Next. Right. Yeah. Next. Yeah. So that's the whole of our consortium member. Right. Next. So whole of the project has been organized into the 7 work packages. Work package 1, specification for the minimum moving block performance standards. The work package 2, the modeling and analysis of moving block specifications using formal method. The work package 3 is on the fail-safe train localization solutions, right, using GNSS-based technology. The work package 4, how to integrate the safe and optimize traffic management with moving block system. The work package 5 is testing, assessment, and demonstrations. So work package 6 for dissemination and the work package 7 for project management. Next, please. So we follow the V diagrams. We start from the specifications, then we got the main work packages, and then we'll do the validate and verifications, right, in work package 5, right. So that's the architecture for whole of the work package. Next. And this is a Gantt chart for the timelines of the project. Next, please. Next, please. Organization structure. So far, we have already submitted 12 deliverables. The 2 work package workshops have been organized, and also the 11 dissemination events has been done, and 8 papers have been published for the Performing Real project. Next. So in the following slides, I will quickly summarize the technical progress for each of the work packages. The work package 1, the specification for the minimum moving block performance standards. Next. So we would like to provide a baseline system specification for ETCS level 3 moving block signaling system, and we would like to contribute to the definition of railway minimum operational performance standards for moving block system. Next, please. So those are the main activities in work package 1. Identify the moving block system and the virtual coupling variants, detail different user cases for moving block system, develop a functional architecture, and also the synthesis of requirements. Next. So that is the deliverable 1.1 baseline system specification and definition we have submitted. Is now available on our website. Next. And also, the second period of work is mainly on the recommendation and standardization to the definition of railway and MOPS. Right. Next. So work package 2, the modeling and analysis of moving block specifications using formal method. Next. So we would like to provide comprehensive modeling approaches for ETCS level 3, and also to develop the parameterizable models to analyze the operation under the movement block, and also to investigate the behavior of the system against the possible hazards. Next. So we've done that definition of the operational scenarios, definition of the specifications, and also the specifications of ETCS level 3 SysML models, and also the creation of the formal models for ETCS level 3, right? So the final work is a specification of all these 3 operational scenarios, integrations-based modeling, and also analysis and verifications of the level 3 properties. Next. So this package is specifically, contribute to X2 Rail 3, and also we have got developed formal models for the 5 modeled function components, 2 languages used, and also combination of formal method to model and analysis operational scenarios, integration-based approaches of UPA model, and also definition of a library usable models. Next. So we have submitted the D2.1, and also the D2.2 is submitted, and the D2.3, right, has already been submitted as well. Next. So the work package 3, that's the method for fail-safe moving block train localization. Next. And we have designed multi-constellations and multi-frequency GNSS processing engines with IMU integrations. We have also defined of the field events in the GNSS context and assessed their impact in position computed from the GNSS processing engines. And also we provide affordable multi-constellation and multiple frequency GNSS computer and perform the data campaigns in real scenarios. Next. So these are the GLS simulate we have developed. Next. And also the field events we have identified. Next. The data campaigns we developed within Rakuba. Next. And also that is the real, devices and the experiment we have done right in the field. Next. So we have collected some data in one of the British railway track line. Next. So the next steps is we would like to execute the validate and testing of the missing field events, complete the simulation scenarios, and also the process data for the real campaigns, and then finalize the deliverable 3.4, the validation test report for the train localization of GNSS using GNSS. Next. So work package 4, that is mainly on how we could use the railway traffic management right together with moving block system. Next. So we model and integrate the TMS. For moving block rail operations, we define the method of optimal traffic management and early warning of hazard conditions in moving block. We also provide a guideline for the future railway traffic management system for moving block system. Next. So we've got 3 main work tasks in work package 4: modeling of signaling and localization, algorithms for optimization, optimal traffic management, and early warning, and which are already completed. And the final one is a guidance on future TMS. Next. So these are the methods we use. We call it the rescheduling tools for moving block system. Next. And that is the early warning of the moving block hazards we have identified in this work package. Next. And also, finally, we have integrated all of this traffic management together with the University of Birmingham's railway simulator. We try to validate our traffic management solutions for moving block system, then to formalize the guidance for the future traffic management for moving block operations. Next. So the work package 5 is mainly on the testing, assessment, and the demonstrations. Next. So we have developed a railway simulation environment integrating University of Birmingham's railway operation simulator and Rakuba's GNSS simulator to test and assess the developed proof of a concept in this project, and also implement the testing routines and demonstrate defined moving block and train localization specifications in the railway simulation environment. Next. So that is the timeline for whole of the work package 5. So now we are on the phase 4, the final integration and the demonstrations. Next, please. So that's the overall architectures we have integrated together using our microscopic railway simulator together with the GNSS solutions for moving block systems. Right. Next. And also we have developed the case studies, right, to validate all of the solutions we have. So we have got a testing site at Milton and Leicestershire in the UK. So the test track consists of 4.6 miles of track and starting from Old Derby to the end of the Stand tunnels. Right. We have modeled the whole of these scenarios either in our simulator, and also we have collected a lot of GNSS data on that test track. Next. So we've done a good performance analysis, right, to see whether the GNSS solutions for train localizations is usable. Right. Next. So the next steps is we will try to finish the integration and supporting testings for railway traffic management, and also the real GNSS data will be used into the platform to better represent the behavior of the system, and then finalize the testing rules. Right. Next. So the work package 6 is more on the dissemination, communication, and the explorations. We have organized a list of the events, right, to disseminate the outcomes for this project. Next, please. And next. So those are the main activities we have on the website, the event, and the workshops, and also publications. Next. So those are the examples of our dissemination events. Next. And also the deliverables for work package 6, right, which have been all submitted to the project portal, right. Next. Yeah, thank you very much.
Thank you very much, and I should admit that our communication about the presentation was before we did know the time frame. So thank you for speeding up and finish in time. Thank you for the interesting presentation, and I would like to give the floor to Gabriele Cecchetti from the Optima project. Please introduce yourself in 2 sentences. Thank you.
Thank you, Matthias. I am Gabriele Cecchetti, and I'm working as a researcher at the Scuola Superiore Sant'Anna in fields of research for computer and communication engineering. Currently, I'm the technical leader of the Optima project. Let's start to introduce some context about these projects. Nowadays, all major railway infrastructure managers are using a traffic management system in their control center for managing traffic, energy, detector, remote control, RTMS center points, and video surveillance system. This system have been introduced over the years without thinking about their scalability or their interoperability. So what's happened is that each country may have a different TMS system, and even in the same country can coexist different TMS. So due to the absence of standard communication interface and the lack of interoperable data structure, they are not fully interconnected with the field, with the rail business service and external service, and that leads to poor operational efficiency. Next slide, please. So the Shift to Rail JU designed as the goal to develop and implement new technologies for rail traffic management system. And it designed the technological demonstrator 2.9 to specify a new TMS, which is based on standardized framework, data structure, real-time management, messaging, and communication infrastructure, including particularly the interface for internal and external communication. So to let to different subsystem application and clients to communicate each other in an integrated way above all with interoperable data. Next slide, please. So the Optima project was selected, and its goal is to specify, design, and develop and validate a new communication platform demonstrator, which should use standardized data structures and processes to manage this communication process between the TMS and the field resource, like the client and the application. So in this way, the Optima is closely linked to Technical Demonstrator 2.9, and its main technical objective of the project are a seamless and dynamic data exchange between rail business service, and the medium for this communication is a common communication layer tested technically called the integration layer. Then the second objective is to use a common data model, which should be the same across all the shift-to-rail participants to enable the integration of legacy and future application into one communication data structure. And finally, standardizing the building block and the workflows inside the control center. So having the same design of operator workstation and application framework that led to install TMS service in a plug-and-play manner. In this way, the optimal communication platform will enable to experiment a new application for traffic management, traffic control, and to allow the integration of new technology and functionalities, like, for example, ATO, moving blocks, so every functionality that has been developed during this year under the Shift2Rail and now A2Rail program. Next slide, please. Here in this slide is illustrated the optimal architecture. At the core of this architecture, there is the integration layer, which is exposing its API, and the communication data model. Then we have on the bottom the data coming from the field. So the Rail Business Service that can be interlocking system, RBC, maintenance service, energy management system, and external service, like, for example, weather forecast or passenger information system. Then we have the TMS service that run inside the application framework. And this service may be accessed by the operator workstation. Next slide, please. As I said before, the integration layer is the core component. Integration layer is a real-time messaging system based on publish subscribe mechanism with standardized topics and interface for internal and external communication between different subsystem application clients. So it led to have multiple clients, integrated automated data exchange process, real-time availability, and you may configure different QoS level service. This integration layer has been enclosed into a wrapper that offers to the developers an integration layer API that led to provide a dynamics, seamless and dynamics exchange between the various services, between the different Optima components. The main service that are offered are the authentication, the authorization, the transactions and the boxing, the logins, and the persistence. In particular, I offer the content of a geographical database which represent the network topology and the relations between its elements, the timetables, and the database of assets, including the vehicles and their features described. Next slide, please. The other core element is the Optima Shift2Rail common data model. This is a standardized and scalable system architecture that starts from a CDM definition that is based on requirements. This requirement may be expressed as Excel file, UML diagram, or XML sheet. Then, through a transformation, the platform-independent model is transformed into platform-specific model. Then with the code and configuration generation tool, which is taken from the complementary project X2Rail 4, is generated protobuf schema that are used by a codec library. The codec library is used by application prototypes Rail Business Service to publish and to decode the data coming from the integration layer to provide and to consume the information. Next slide, please. In Optima Consortium, we have three infrastructure managers, Adif from Spain, RFI from Italy, and Sprava Senekli from Czech Republic. Having three infrastructure manager is a richness because we can demonstrate the interoperability between different data. So we have to deal with the problem of managing data coming from different sources. So we have created a one virtual track that maps on the physical track that is the railway line from Ventimiglia to Albenga, controlled by RFI. The data collected by Rail Business Service and External Service, once it's collected, is mapped on this virtual track by a specific software. Then, of course, for cybersecurity concern, is anonymized and then is published to the integration layer. Next slide, please. Here you can see an example of data that is coming from track circuit and is published to the integration layer API. If you click here, you can see that the data is transformed, in this case, in a JSON format and is sent to integration and can be easily decoded. Next slide, please. The other core component is the application framework. The application framework led to have a uniform deployment and operation of TMS service. It integrates virtual machines and containers. Virtual machines are managed by VMware vSphere software, and containers are based on the standard Dockers. In this way, is offered the isolation of application, and the control is all in the hands of the infrastructure manager. It offers standardized interface that let the application to communicate with the rest of the business service or with other application through the integration layer or through a dedicated REST API. On the right part of the slide, you can see the typical cycle of software deployment, where application vendor can upload their application to the software repository, and that can be done by the system integrator that can configure in the deployment the application. And all the applications are kept inside the application framework repository. Then a system operator will operate running different instances or even multiple instances of the application inside this application framework. Next slide, please. All this structure is running on an hardware composed by a cluster or 4 servers. These 4 servers are organized as a hyperconverged cluster where is installed the vSphere software. And in this structure, we have several virtual machines. Each virtual machine is dedicated to the different service of the field, for example, interlocking, RBC, maintenance, and so on. And we have also the application framework that is containing the VM or the Docker container for the different application provided by complementary project or by any other operator who want to test this communication platform to check if the application is compliant with this standard. Next slide, please. A particular application that is running inside the application framework is the integration layer gateway developed with X2 Rail 4. The goal of this integration layer gateway is to let the application running inside X2 Rail 4, that they have their own integration layer, to communicate with the integration layer of the Optima project. They connect to the gateway through the STOMP protocol, and through the gateway, they get data from the Optima field, so from the Rail Business Service and the external service. This is an example of a federation between different systems that are using also different integration layer, and it contributes to reach the goal of validating the interoperability between the Optima Common Platform demonstrator and external prototypes coming from different project. So this will be one of the biggest achievement of this project. Next slide, please. And so now we are at the conclusion. The Optima platform demonstrator development is completed, and now we are in the last months of the project, and we are validating it both internally and externally with the external prototypes. We are validating against several scenario tests, and KPI has been defined to validate the platform. So we are assessing the performance until normal and stress load condition, even in presence of error injected to the system. Prototypes of complementary project X-Ray4 are also being validated through the gateway, and that let the external integration layer to communicate with the optimal integration layer. Once that the optimal communication platform will be validated, it may be used as a reference demonstrator for any future implementation of this new TMS paradigm, which is based on Technical Demonstrator 2.9. Next slide. Here is just showed the group, the consortium of Optima, which is composed by 16 partners, which have well worked until now. That's all about the Optima project. Thank you to everyone.
Thank you very much. And now, last but not least, I would like to give the floor to Daniela Ristig-Duran from the SMART2 project. Please, Daniela.
Hello, thank you, Matthias, for introduction. I hope you hear me well.
Yes.
Great. Thanks for introduction, and thanks for invitation to present the results of SMART2 project. My name is Daniela Ristig-Duran, and I am a senior researcher and lecturer at the University of Bremen. And also full professor at the University of Niš in Serbia. Both universities were partners in this project. I was the coordinator of the project SMART2, and I'm glad to present our final results because the project just finished on 30th of November. So we submitted all our deliverables. A lot of work is behind us and a lot of results. But I decided to present in this short time available the most attractive results, and somehow I hope it will be the interesting last time presentation in this slot. Please, next slide. So our project SMART2 was dealing with development of advanced system for autonomous obstacle detection and track intrusion in railway. As such, we are assumed to contribute to future development of ATO with respect to obstacle detection when the time will be ripe that obstacle detection is integrated. So in our project, we were not concerned with integration of our system in ATO, but of course we had in mind that future developments, and we hope that our results will also give some directions in that way, in direction of development of obstacle detection in railway, which is necessary or which is critical or crucial for railway safety, and then will be crucial for ATO. Please, next slide. So we started from results in a previous project SMART, in which some of the partners were also dealt with obstacle detection, but only with the onboard system. And we achieved quite a good result in Project SMART, as confirmed by reviewers and a number of publications. And of course, we confirmed the general knowledge that even the perfect onboard obstacle detection system is not sufficient, because even the perfect onboard system cannot see beyond the field of view and cannot see, for example, beyond the curve. So our task in SMART 2 project was to suggest a possible solution to overcome that problem, and so to enlarge the area for obstacle detection. So in simply speaking, then our goal in SMART 2 project was to suggest possible solution towards a holistic obstacle detection in railways. Next, please. And our proposed solution was, I don't know what happened with the slide. I hope it does not bother you. There is some background text. So our proposed solution was to advance further onboard obstacle detection system that we already developed in SMART, and to complement it with two additional systems. One, trackside obstacle detection system placed usually on level crossings, and another which is drone-based, so unmanned aerial vehicle-based system. This is, of course, one possible, one proposal to go towards the holistic system, but what we did for a drone could be done, for example, with a fixed trackside system. So the idea was main on that to complement onboard system with additional system. Next, please. Which would then be integrated together, so to communicate to the same central decision-making unit, so that each subsystem would recognize obstacles in its field of view, and then the results would send to a cloud implemented decision-making system, where the final decision will be made on whether there is an obstacle in front of train. If there is, where is the obstacle located, how large the obstacle is, and what is the class of the obstacle. Next, please. And as I said, the main system of our holistic system is, of course, onboard system. And we started from advancement and improvement of onboard system in already developed in SMART project. So we built on lessons learned there. And based on all that, in this slide, you can see the final prototype of our SMART 2 onboard obstacle detection system. As you could see, our system uses different types of cameras, vision sensors, several RGB cameras, thermal camera, and sphere camera. The main idea of using multiple vision sensors is to build a redundant system and to use the advantages of each and to cover the obstacle detection in different illumination and weather conditions. All sensors are integrated in custom-made housing, which is designed and manufactured so that it can be easily mount and demount from the different test vehicles, different locomotives. And as you can see in this slide, the onboard system was mounted on an operational train owned by Serbia Cargo. And we achieved the demounting and mounting in time under 20 minutes, which was one of the main criteria set to us because we were allowed and permitted by Serbian Railway to perform a test in operational environment. The requirement was that, of course, we should not disturb the normal functioning of the railway. So next, please. And of course, there is the hardware. Hardware means that we used usual sensors that in such obstacle detection systems, integrated them. And then the main goal, the main work was on development of software that will be used for obstacle detection in different weather illumination conditions, and with which it will be possible to achieve the obstacle detection in a long range. The software we developed is based on artificial intelligence. Important is to know that we develop one model which can be used used for different vision sensors independently of the type. But of course, we started from the model which was built for RGB cameras, and then we did a lot of adjustments to enable use of this model also for different type of cameras, thermal and sphere. Basically, our software consists of two main parts, as shown here in the slide. The first part is object detection, and the second part is distance estimation. In object detection, we implemented, tested, and finally decided on one state-of-the-art bounding box object detector based on a deep learning, which is appropriate for real-time use in application such as obstacle detection in railway. The main criteria for all object detectors that we investigated, that we played with, was that they are so-called bounding box based, which means that they give as an outcome the box of detected object in the image, and this box together with the object class was input to the second part of our software which we developed, which is in principle neural network based distance estimator, which was trained so to learn the relationship between the size of the object bounding box and distance. Please go forward. And of course, because we developed a software which is artificial intelligence based, the most or the challenging, the problem was to generate appropriate data set. So we started from the custom-made data set that we already developed in Project Smart, and we were very happy that we had that, because our Project Smart 2 started just after the onset of Corona pandemic, and due to all traveling restrictions introduced, we could not perform our field tests recording as planned. It was only in the last year of the project that we could go out in operational environment to do the new recordings. So we were lucky that we had a data set of real world images recorded in previous project, and we use as a backup solution work with that data set, modified in a particular way that it could be used in a Smart 2. Of course, we had also backup solutions for some recordings, and we could not do the joint recordings as planned, but individual partners managed a lot of individual recordings, and we managed also to augment continuously this data set with the new recordings, for example, with the images of sphere camera, which we didn't in Smart. Anyway, the data set of Smart 2 consists of large number of real-world images recorded in operational railway environment, the images recorded in different illumination and weather conditions, and the images which contained real-world objects of different classes, which are potential obstacles in railway environment. Next, please. But because we had that problem of not being able to do the field test recording, even though we had a smart data set, it was not sufficient to retrain the models and to improve the results. Because of that, even though it was not in our description of action, we introduced the new tasks of generation of synthetic images, so to augment our data set. And I'm pleased here to show some of results, because we really achieved good results and new for this field, because in contrast to automotive industry, where there are a lot of data sets already available for autonomous obstacle detection, and where there is a lot of work on also synthetic data set, in railway field there is only one data set available, but even that one is not convenient for obstacle detection, because does not have annotated data data with the objects and associated distances. So what we did, we of course had to go forward by developing our custom data set and augmenting it. And in different methods, we achieved augmentation, as you can see here in a slide on the left side, augmentation with the images of objects which are hazardous for railway, but that cannot be easily recorded in the real world environment in our field tests. For example, here you can see images of horse on different distances. So we augmented our data set with the images of important object classes, and we covered with our augmentation a large range of possible distances. On the right side, you can see the synthetic images of fallen trees, object from the class of fallen trees, which are particularly hazardous for railway, as we know, but which are really difficult to, or was for us difficult to record in a real world railway operation. So because of that, we created different methods to create synthetic images. Please, next. And thanks to this, we managed to come to the end of our project to perform evaluation in a real-world environment. Here you can see illustration of our evaluation route. The route, the field evaluation tests were done on the Serbian part of Corridor 10 from Serbia towards Greece. We covered the route of about 11 kilometers. We, as you can see here, could test all our subsystems. The next, please. And we achieved the results. Here is a summary of some results. So we achieved online rail track detection, straightforward as well as curved. Beside the rail track detection, we also developed algorithms for track intrusions, so to monitor whether the objects enter the clearance region or not. When it happens, as here in this image, then the detected rail turns from green to red. We achieve long-range detection. Here you can see the result of 1.3 kilometers detection. We achieved detection in real-world environment of different classes such as fallen trees, and we achieved also detection in night conditions thanks to our sphere camera. Next, please. And the very last two next slides, without going into details, of course, as I said, we used all these redundant sensors, and all of them were looking on the rail track in front of the train, and of course the data of each was processed, and then it happened that different sensors provided different results on object detection and sent to our decision making in the cloud. So it was necessary to perform sensor data fusion, or in other words, to perform decision making, so to make decision out of all these inputs coming from different sensors, which would be final, and as such would be in future sent to train controller. So the decision on what is the object there and on which distance. And for example, here you see the illustration of onboard decision making, where three different sensors, three RGB cameras, because of different zooming factors, saw different objects in the scene. Some of these objects were the same, but detected or with different estimated distances. So using some our developed decision-making algorithms, after matching the detections, we managed to achieve the results shown here in the slide. So to have the final result on a particular object. And please, the next slide. The same, of course, we did for different systems. So the previous slide was for onboard decision making, to make the final decision starting from the outputs of onboard sensors. But of course, it was needed also to make the final decision starting from the outputs coming from drone-based system, for example, an onboard system, because in some parts, the field of views of these two systems didn't overlap, but in a parts where the fields of views of these systems overlapped, it was necessary to make decision making, and it was done following decision making algorithms developed and so-called matching of detections. And the very last slide is about the partners who were involved in a Project SMART and who achieved all these great results, as proved by the number of publications. So the mainly responsible for software development for drone and onboard was Institute I'm coming from at University of Bremen. And the partner from Niš, University of Niš, was the mainly responsible for manufacturing of onboard housing and also for performing or evaluation through the cooperation with Serbian Railway. We had a partner from Bremen, OHB, who was responsible for all these cloud implementation and sensor integration. Partner SOVA was responsible for sphere sensor. Partner from Romania, Cluj, was responsible for a drone-based system. Focus from Slovenia was responsible for a trackside system that I did not mention here because using traditional LiDAR-based detection of objects on the level crossing. And a partner from Newcastle University was our, let's say, theoretical partner who was analyzing the requirements for use cases and requirements for such a system at the general level as well as at the demonstrator level. So that was all from my side. Thank you very much for your attention.
Thank you very much. Meanwhile, with the small delays adding into a bit of a lot of so. At the end, we a bit eat up our Q&A session. So I think please let us know your questions via email. And I think I would like to thank you all these interesting presentations and thank you for your attendance. I think this session was a good closing for a busy year in these projects live, and I would like to give the floor to our executive director Carlo Borghini and to our head of program management Giorgio Travaglini. Thank you.
Good afternoon. What 3 days? We are still my people in my office because this we are the broadcasting from the Europe's Rail HQ. I've been traveling with these days, but Giorgio has been following up. I was following up while I was traveling, so it was quite complex. You know, these 3 days have been quite unique. There was an Italian writer, you know most probably because like me, you studied in Italy. Started one of the major I Promessi Sposi, I will say in Italian because I don't know any other title. And his beginning is to say to the 4 readers that will read my book, and this book has been read by maybe millions of people, or at least the Italians. I think have been done movies and many other things. So I think this Europe's Days have been also a great opportunity to share with the rail community different level the work we have done in the past. It's the last event of this year. This year has been plenty of events. We started, I think, at the beginning of the year. Maybe the first event was in the Connected Europe Days in Lyon. Yes. After we moved to the WCRR in Birmingham, where at the world level we show Europe's rail and ship rail program results. We had later on Inotrans, and there I think the demonstrator on ATO, Geo for preparedness, as well as demonstrator on language, and the VR glasses for the dock, I think have been extremely interesting. And finally, we had the TRA mid-November in Lisbon. But these specific days, I would only focus on something that is important at the moment. We have in Europe energy crisis going on. We know that there are the concern expressed by many operators and infrastructure manager on how we can operate the rail system, both for passenger and for the freight business, especially when we have the ambition to make rail the future backbone of the mobility and transport. And maybe, Giorgio, I would ask you to recap what everyone can find inside the Shift Rail projects about the energy aspects, and not only on the long term, because clearly we can work, but the crisis is today. So I think we have a lot of works that have been done during the previous year in Shift Rail that today can be useful. So maybe you can focus also on this.
Okay, thank you, Carlo. Indeed, I think everybody has seen during those 3 days that we had also this little fil rouge of energy efficiency and how we can handle in this period the energy itself and how we can reduce its consumption. And maybe just to recap, on the first day, we have seen that they exist, the solutions, we have demonstrated them in order to reduce the weight of the rolling stock components. And those reduction of the weight we have shown to you, it is done on the car body shell, and it is done on the running gear through the use of a single axle. But not only. So IP1 have done other elements that have not been presented in this first day in order to reduce the energy consumption, starting, for example, from the traction system. Another important aspect that we have seen the first day, still speaking about rolling stock, is that components on the train, like doors and interiors, where immediately you could not maybe imagine that it's linked with energy reduction. It is actually because of the thermal masses, thermal components and properties of the door on one side, but also there again on the lighting factor, if you can reduce the weight. We are seeing in the CCA, still on the first day, that a new approach also on integrating data coming from the rail environment into the traffic management system can help to optimize the traffic, and therefore there is also a direct link with, let me say, a better efficient management of the train, so less waste on the energy consumption on maybe, for example, empty train runs. And we also seen in the CCA that an holistic approach is also needed, because there are plenty of energy components here and there, but we need to look it in its overall system, and we need to measure it with important KPI indicator. On the second day, we have seen the infrastructure side, and on the infrastructure side, clearly you have seen as well that we have technology ready. For example, on alternate current, on the transmission system, different type of transmission system solutions that can, let me say, leverage the traction power, controlling both the power that go back into the grid and the voltage imbalances. And this what helps, but helps also to reduce the cost, because you will have less penalties we have seen on the energy bill if these are correctly managed. And then it's important also to correctly monitoring the flow of energy. And we have a solution, which is the smart metering that has been presented as well. And this will allow to identify where in the network losses exist, and then intervene with probably very easy and solutions that we can apply already today in order to improve the efficiency of the energy itself, and also to reduce where it's important the demand, the peak demand of energy. In IP4, still on the second day, well, IP4, we have simply seen the technological possibility to bring up a multimodal system whereby we would attract more passenger and customers to rail. And by doing this, we all know that rail, it's already per se a more energy efficient transport modes compared to road, for example. And then also at the end of the second day, we have seen that technologies in digital technologies also needs to look into how to better use the energy management. We have been discussing, for example, blockchain technologies. Also there are ways in order to create blockchain and consume less energy. And more importantly, I would say, it's also the use of automatic train operations that has been also discussed today. So on how automatic train operation can really and this is a solution already available, at least of JOA2, can reduce significantly the energy consumption. And IPX, together also with IP2, it's also looking into JOA4. And in IPX, the idea is really ATO over ETCS over all the network, which will really allow an easy transition of energy. And then today on the flagship, on the Innovation Program 5, you have seen also on freight how we can significantly reduce the energy consumption, starting from a better management at maintenance level, so also there to identify faults and be able to correct and reduce the energy losses, but also using different type of harvesting systems that we have already tested and are ready for integration in the market on, for example, harvesting technologies installed on axles, or, for example, using batteries technologies as well on freight locomotives. And we have seen there is, let me say, also a return on investment on this, even though it's not immediate, but on a long term, there is a return on investment. And then finally, today, I will not go too much into the details because you are fresh from the IP2 presentation, but you clearly have seen how we can put together all those different technological components that would reduce the energy consumption, for example, with automated train operations, but that will be integrated with adaptable communication systems, so systems and together with training integrity, so with systems that also reduce the cost because we are removing components from the equipments from the infrastructure. And another, and I would say the last interesting part that I would like to mention is today from the IP2 presentation on the TMS. It's also the fact that ATO cannot be just treated alone. I mean, ATO will help for reducing the energy, for increasing the energy efficiency of a single train, but we need to look at a system level and at a network level, and this is the role of the TMS. And we need to find the right balance between the two, of course.
Thank you, Giorgio. I think you brought up two important aspects. The first one is the system approach. And I think I'm really happy to say that the governing board endorsed our proposal on the fact that the system pillar within task 1 of the system pillar, we look at the aspect that we discussed today. You presented now in a summary, but has been the fil rouge, as you said, during the 3 days of the Europe's Rail Innovation Days, of this first edition of the European Days, Europe's Rail Innovation Days, about energy. So the system pillar will take care of bringing to life all these type of solutions and also packaging them with the system approach. So I'm happy to say that the work has been starting and they will be discussed with the sector within the overall task 1, and maybe they will become a dedicated task in the next weeks or months. The second one, I think that you point out, is that all these work are fundamental because they contribute to mathematically and are being measured to show that there is effectively cost efficiency and energy efficiency coming up from this, but have to be deployed. And I think the deployment of the solution is really the fundamental component. We should shorten the time to market of the solution that we develop. Some are becoming already, we know them inside we have seen them also in Innotrans, inside the products that the suppliers are developing. I think we need to act much faster. And I hope also from this point of view, the system pillar will help. And the third aspect is that the innovation pillar of the Europe's Rail will continue in a more systemic manner to work together with the operator, infrastructure manager, and the supply industry, research community. We are just signing now the grants that we are materializing all these efforts ongoing for the last months, and it will continue for the next 4 years to deliver the major change we want to see. So I think this first edition of the Innovation Days of Europe's Rail are really showing first of all, on what we have built upon Europe's rail, but also what is available that has to be considered for the deployment. And I think all the Europe's rail program and previous issues rail have been designed around the logic of impact and a continuous chain or ideas or exploring ideas of new rail research innovation solution that can be deployed in the future years. Well, I would like to only to conclude these days, well, first of all, thanking all the staff of the JU, Giorgio first, because, but all the staff, all the senior program manager, the assistants that have been working during the last 3 days behind the scene, ensuring that everything was working fine. The communication department of Europe's Rail, also the colleague of finance and legal who were behind to check that everything was fine. So all the team of Europe's Rail that in these days have been working together. I would like to thank all the speakers and the projects that have been working to deliver such results, and they took the time to present these results to the rail community in the past 3 days. It's a major effort. It's a major effort because one of the key objectives is openness and inclusiveness, is disseminating the results, creating opportunity for new connection, creating opportunity for new ideas, bringing the results to the market and implement the results in the rail system. We want to have the next generation of rail system driven by performance, safety, and security. And I will not talk about interoperability because it should be there by design. So there should not be thought about this. So once again, thank you to all of you from my side, and I believe also from Giorgio's side and the team. Once again, thank you to all those that have been following us also in the next days. All the recording will be made available also later on, will be accessible also via social media. And to me, I would like only to wish all the best for the incoming holiday season. And we hope also that the current crisis we are suffering from in Europe will be solved. Thank you.
Thank you.